Welcome to acid and base equilibria. These are the equations that the ionization of water is equals to H3O or H, then multiplying the products together to give you 1.10 times 10 to the power negative 14. pH is negative log of the concentration of acid, pure H the same thing, and then the combination of concentration of acid then gives you acid, and then that is all the equation you need to know. Percentage ionization is equals concentration initial and versus the concentration of equilibria of initial, and then this is the dissociation of acid there, and then you'd find that dissociation of acid, dissociation of base have more or less similar equation, but the numerator is acid and then the denominator is actually the base. And then you multiply the constant K constant and B constant, gives you 10 to the power negative 14, and then the negative log of that will also be equivalent to 14. So that's the power, which means that you pKa means the dissociation constant of acid. You multiply that by negative log, so it's negative log, then you put in the K, the value inside. So in this case our answer should be positive 6 there. pKa should be positive 6. So I don't think I have enough space to write the value, but you can see exactly what is going on. So make sure that you know these equations by heart, all of them. That is for the chapter. So every chapter you should be equivalent. And how do you know all those values? By memorizing them and also by doing the problems, as what we will be doing today. So let's come to activities 16,13. You're required to find the difference between Arrhenius and Bronsted Lowry of acids. So acids, we have three definitions. The first definition is Arrhenius, followed by Bronsted Lowry, followed by Lewis. So Lewis is the holistic better definition. So it defines acid in a most holistic way. Now let's go according to Arrhenius and see what is the difference. According to Arrhenius, an acid is confined to an aqueous solution. So you need to have it in aqueous solution to determine if it's an acid or not. So that definition had some few limitations, but remember in history we start with a more minimal definition and then move on to a more specific, more generic. So that's how the definition is in terms of sciences. So you just define what you can, and then over time there'll be more research, there'll be more effort by different people, and they can either discard it or they can improve it. So Arrhenius' definition was not discarded, though it had limitations, because most acids really do participate in aqueous environment. So that's it. So Arrhenius acids confined aqueous solution. It has to dissolve in water to increase the concentration of hydrogen ion. Now Bronsted Lowry had to add to that, said acid applies to any physical state and that acid is a proton donor. By that way it means that it can participate in air, it can participate between solid to solid, aqueous to aqueous, something like that. So that's more relevant. Then let us look at the Bronsted Lowry as a proton donor. So we're looking at the problem that ammonia and hydrochloric acid. So what will happen? So we have ammonia there, which is actually gas, reacting with hydrochloric acid. In this case is also gas, and then that gives you in this case that will be ammonium, so that will be ammonia, irrespective of the phase where this gas aqueous, so just write the products for simplicity, unless we are required to do so or unless we're given. So in this case, let us see what behaves as Bronsted Lowry. So the BL there is for Bronsted Lowry. So hydrochloric acid, because it donated hydrogen to ammonia, then that means that the hydrochloric acid is hydrochloric acid is a proton donor, so it is an acid. And then ammonia, because it received one hydrogen to become ammonium, then that means it's a Bronsted Lowry base, because it accepts. In order for you to donate, there has to be something that will have to accept. So it accepts hydrogen from hydrochloric acid. So this is your homework. Go through. You must remember to pause the video so you go through the problem. In this case, you have the conjugate of a base, conjugate of an acid. So you have to determine which one is an acid and which one is a base. So in this case, you can see it's you must also check the left hand side in this case. Unfortunately, the arrow is just forward. It's supposed to make it reverse reaction as well, but let's take it in the reverse way. It's hydrochloric acid. It's an acid because you can see it's going to donate hydrogen to water, and then it becomes a Bronsted Lowry acid, and then the water there becomes hydronium, so in that case it becomes the water is a base because it has received. On the other right hand side, you see that the hydronium H3O plus will donate hydrogen to chloric ion negative. Then that will have to be that is the reverse part will have to, the hydronium becomes water, so the chlorine becomes a Bronsted Lowry base. So you do the same for exercise A, B, and C. So that was just a mere example, and then you take on the example and solve. So those are conjugates because there's a difference of one hydrogen. So whenever you look at aqueous conjugates or in a gas form, just look for where there's a difference of one hydrogen. So hydrochloric acid and the chloride ion, that creates a conjugate, so the one is a conjugate base of the other and the conjugate acid of the other. And then water and hydronium, there's a difference also of one hydrogen. So in that case, the difference of one hydrogen creates a conjugate. Other conjugate base because it received, or conjugate acid because it donates. So it's one hydrogen short. Let us look at 16,27. If a neutral solution of water. Remember, you have to pause to understand the problem, because I won't have to pause for too long, and I'll go straight to the problem. And then you have in water, the only source of hydrogen is autoionization. So in that case, that means the concentration of acid and concentration of hydronium is the same. As the temperature changes, the dissociation of auto-dissociation of water or autoionization of water also changes. In this case, like when it increases, it also increases. So we have pH negative log concentration of hydrogen, and then that's the equation that we substitute. We have a pH at 6.63, giving us minus log concentration. So finding the concentration of hydrogen will be base 10 to the power negative of the pH. So that's the most equivalent way. So you must know how to do it really fast, and then the answer there gives us it's supposed to be 2.34 multiplied by 10 to the power negative 7. So that is the molarity. So the very same molarity there, the hydrogen ion is equivalent to hydroxyl ion. So the acid and the base, because it's supposed to be equilibrium, then that means that that is, so the hydrogen there is supposed to be 2.3 multiplied by 3.4 negative 7 molarity. What has actually happened, the key W there. So one of the equations up there supposed to be hydroxyl, So I remember that hydroxyl and hydrogen potential is actually the same thing, you know. So that we multiply by 10 to the power negative 7, all of that multiply by 2,3 to the power 2.34 multiplied by negative 7. So that means that point of correction there, you see the concentration of hydrogen is equivalent to concentration of hydroxide. So you can even make double of each because it's all the same, you know. But you can also put there as concentration of hydrogen ion is equal to concentration of hydroxyl ion, and facts that they are almost the same thing. So one other fact could be that concentration, number of mole over volume. So when you increase temperature, so the water will evaporate if it's open system, and then number of moles would be the same. Then you expect an increase in concentration from 1.0 times 110 to the power negative 7. It will give you 2.34. And then you also have to calculate concentration iron falling solution, indicating whether it's acid or base. So A, we have hydroxide there. Remember to pause the question and then solve the problem. So pausing the question there, A, we are given hydroxide. We are given the base in this case. So the base is equivalent to 0.00045 molarity. So giving 45 molarity there, we have to find the concentration of acid given the base. So concentration of acid there will be dissociation of the acid, dissociation of water, constant dissociation of water over the concentration of the base, you know. And then that one there will give us the concentration of acid will be Kw will be 1.0 multiplied by 10 to the power negative 14. Okay, so that divided by 4.5, so we are writing the value given there for the base in exponential form to the power 10, that is negative 4, and then that will give us a value of, using your calculator. So always remember that when you divide on top, put brackets, and then the numerator, when you're done the numerator, bracket, and then divide by the bracket of the denominator. So as you can see, 2.2 is less than 1.0 multiplied by 10 to the power negative 7. So that gives you it's basic. So that's one way of checking whether it's basic or just looking at the neutral value, concentration of acid. If it's more than, then it's an acid. If it's less than, so remember when it comes to negative numbers, less than should be greater in terms of negative power to the power negative. If it's greater in terms of negative value, then it's less. If it's less in terms of negative value of the exponent, then it is greater. So check about the negative values of exponents. And then there you can also use pH, as I said, or the pH of that concentration. You see that it's 10.65. That's concentration of acid. So that's actually basic, you know. So those are the ways you can go through and solve the problem. So it's the same thing. Okay, so let us come back to the other evaluation, B. So in B there you can see that B, we have hydroxyl concentration which is the base concentration. So the base concentration there, they say it is 8.8 multiplied by 10 to the power negative 9. That is the base. We also going to do the same thing that what we did in problem A. We find the concentration there. We have the concentration of the acid. That would be Kw over the concentration of the base. So that's the correct formula. So that's a formula that you should actually memorize. So you exchange, so according to each. So 10.0 multiplied by 10 to the power negative 14, that's kW value, and then the concentration is 8.8 multiplied by 10 to the power negative 9. So that one there again, let us see what value is going to give us. We'll see that we have 1.14 multiplied by 10 to the power negative 6. So that is actually, that's molarity for the acid. Then there's more acid than the base. So that is greater, that's 1.14 times 10 negative 6 is greater than 1.0 power 10 negative 7. So that's acidic. So the next question there, it says that the hydroxyl is 100 times greater than the H protons. So that means that the base is 100 times greater than the acid. So once again, calculate the concentration of the acid. So that problem said because one is 100 times greater than the other. So what will happen in this case will be that late has a concentration, the small one, let it be X. So the bigger one will be how many times of the X it will be. So please know this this way of solving problems. If you say the pawpaw is 30 times bigger than the mango, then let the mango be X, and then let the pawpaw be 30 times X. So it's going to be 30X. So let the small one get an X, the big one will be 100 times the smaller one. So that's how you're going to solve this problem, a similar problem like this in the future. Alright, so let us see. Now we have kW, we have let the smaller value, which is the acid, to be X, and then the base, which is OH, to be 100X. Now finding the products, the kW's, the products of the concentration of acid and concentration of the base. So that will be X there, multiplied by 100X. So we know that all of the products of base and acid should not exceed 1.0 multiplied by 10 to the power negative 14. And then we simplify, that will give us 100X. That should be 100X. That will be 100X times X, that's 100X squared, to give us 1.0 to the power negative 14. And then we saw for X there, that will be it will be our right hand side divided by 100, which is 1.0 multiplied by 10 to the power negative 14, and all that divide by 100, and then we root that answer. So rooting that will give us 1.04 multiplied by negative 8. So once again, you can see that the molarity there is less than the molarity of the acid is less than 1.0 multiplied by 10 to the power negative 7. So molarity is less than 1.0 multiplied by 10 to the power negative. That's the neutral part. So if it is less than that, then it's going to be basic in terms of the concentration of acid only. So if it's concentration of base, then you have to reverse the object, but stick to, so remember pH is about concentration of acid, so use concentration of acid as a formula. So that one there, 16,30 would be homework. Alright, now we have another question, 16.31. They said at freezing point of water, which is 0 degrees Celsius, the kW, the dissociation of water, ionization of water constant is 1.2 multiplied by 10 to the power negative 15. So you can see that kW there has decreased with temperature. And then also we look at the neutrality. Neutrality means concentration of acid is equals to concentration of base. So that means it will be x squared is going to be kW. So it's going to be 1.2 to the power negative 15. So we have to solve for let us solve for x there. Remember our x is concentration of hydrogen and concentration of the base. So that means that x squared would be the root of the kW. So finding the root that using a calculator, you'd see that it will give us plus or minus 1.2 multiplied by 10 to the power negative 15. That once again will give us a value. We check at the value. Remember, we just need to calculate the concentration. So by that answer I think we'll be done. It is 3.5 multiplied by 10 to the power negative 8. So once again you can see the molarity there is less than, so the acid will be concentration there of acid is going to be concentration of hydroxide ion, and that is going to be 3.5 multiplied by 10 to the power negative 8. So that will be our answer for both acid and the base. And then let us go to the other question. So this question there requires us to do a lot. So it requires us to complete a table. So that gives us a lot of skills that we'll have to do in this case. So the skills there that we need to find out is filling, given one value, then we should transcend into other values and determine if the row has to do with acid or base. Is it acidic or basic? So I'm just creating a table there so that we put the values. Unfortunately there's not much space, so what we're going to do is that we're going to put letters on each block as we continue to solve. So let us look at the one. Given the pH of a normal arterial blood, which is 7.40, at normal body temperature, which is 37 degrees, and then we have the dissociation of water there, the acidic dissociation. So you can see, and then we should calculate the concentration of acid, concentration of base, and P, potential of hydroxyl, and so forth. Alright, so let us look at the space A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. So our job is to fill up the space. So we start with the first row. The first row there, we're given the pH. The pH in this case, we have pH as 5.25. So we can go straight. We can go straight to D, since the pH is 5.25. So that means our value for D is acidic. It's acidic in this case. So pH is 5.25, and then we have the D, which is acidic. So you put that value there, fill in there. You remember, when you're doing this on your own, you need to complete the table. Don't just watch. You have to be hands-on. Do exactly. If you see any error that I've detected, you let me know. Put the values on the comment, or come back to me through an email and so forth. So you can see that pH, that would be 14.00 minus 5.25. So the precision is to the decimal of 2 digits. So that will give us 8.75 there. So that is 8.75 pure H. So pure H, our value A. So A there is filled. So we need to fill in H. Concentration of hydrogen ion. So that hydrogen ion is going to be 10 to the negative pH. So that means that it's going to be 10 to the power negative. Our pH is 5.25. So that's how we find concentration given the pH. So doing that will be we check in the value again. Our value will be 5.6 multiplied by 10 to the power negative 6 molarity. So that one there is a value for C. I think that should be B, if I'm not mistaken. Yeah, that should be B. So B is concentration of acid. So concentration of base, we need to divide Kw divided by the acid. So Kw divided by the acid will give us the concentration of the base. So Kw divided by concentration of acid. Concentration of acid there is 5.6 multiplied by 10 to the power negative 6. Yeah, concentration of acid there, not OH. Point of correction in that case. So that will be concentration of acid. Yeah, that's concentration of acid, not OH. So concentration of acid there. So that means that we have 1.0 multiplied by 10 to the power negative 14, all divided by 5.6 multiplied by 10 to the power negative 6. And the answer there, we should be, if you use a calculator there, it should give you something like 9. Should be 9 point something. Yeah, okay, it should be 9. Just let me calculate. Yeah, it's gonna be 1.8 multiplied by 10 to the power negative 9. That'll be exponent negative 9. And once again, you can see that is the second one. That is our value for C. So it's filled up, and then pure H, that's what we are given, is 2.02. So 2.02, that is the second row. So we are on the second row now. 2.02. Then we need to find pH in this case. So pH is going to be that, okay, minus that to give us POH. That is 11, that will be 11,98. So pH, that means the potential of hydroxide. That will be the potential of hydrogen minus potential of hydroxide. That is to get our pH there. So it's 11,98. And then we have the concentration of acid. So that will be our value for E. The concentration for the acid there will be 10 to the exponent negative pH, which is give us 1.05 multiplied by 10 to the exponent negative 12. That's molarity of the acid, and then that will give us value F. So we fill in value F there on the table. F is given, and then we turn into the next question. So pH there is 11,98. That's basic. So we go in the table there, the last option on the table, that should give us as H. So that is H there. Alright, so we go to H, we are done. So we go for G. So we need the concentration of hydroxide. Once again, hydroxyl will be 1.0 multiplied by 10 to the power negative 14, and all that divided by concentration of acid, which is 1.05 multiplied by 10 to the power negative 12. So that will give us, using calculator, that will give us 9.5 multiplied by 10 to the power negative 3. So that's once again molarity. So looking at that, you can see that it's greater than 1.10 multiplied by 10 to the exponent negative 7. So that actually gives us the idea that concentration there is less, the of acid is less than 7. That's also basic, and you can also use the log for the base to determine the pH as well. Alright, so that one there, we have all the answers on the second row. So we move on to the third row. The third row there, we have all those values there. So remember that in our value we have 4.4. So we're going to look at pH is going to be a negative log concentration of the acid. So acid there is 4.4 multiplied by 10 to the power negative 10. So that's the concentration there. Then that will give us 9.4 that is our value for pH, our I value. And then we go back, and then we know that it's basic by the value greater than 7 pH, so that gives us the L, the acid of basic, so it's gonna be basic. And then we go on a basic, that is L, and then we go on and solve the pOH to find the pOH value. So because we have the acid there, it's gonna be 14.0. So 14.0 minus 9. That's potential of the base. That's 9.4. So we'll see that 14.0 minus 9.4 to give us 4.6. So that's a pOH is 4.6. That's our value for J. So fill in the J there, and then we also come to the value provided. That will be, we need to find the concentration of the OH. In this case, the concentration of the base is to be 1.0 multiplied by 10 to the power negative 14 over the concentration of the concentration of the acid. So we check from the table there provided, concentration of acid is 8.5. But I don't know if I picked that right. Let us just see. 8.5 multiplied by the concentration of the acid. But you can see there's a contradictory. We have concentration of acid as 4.4 multiplied by 10 to the power negative 10. Yeah, multiplied by 10 negative 10. Yeah. So in that way there, it's going to give us 2.3 multiplied by 10 to the power negative negative 8 in this case. So looking at our values there for the third part, so that's the fourth row. We have concentration of acid is going to be 1.0, because we are given the concentration of the base. So 1.10 to the power negative 14 divided by, that is our value, 8.5 multiplied by 10 to the power negative 8. So it's 8.5 multiplied by 10 negative 2. So that will give us the value of, that will be the value of 1.18 multiplied by 10 to the power negative 13. And once again, that's our molarity. So you always give the correct unit for whatever concept you ask. So there's the O, that will be our value for O. So when you find that it's in the real table, you have to replace the O with that value that we've calculated. Then now we have to find the next value on the table. What we need to find, what we're given there. So finding again POH. POH is going to be the minus log. So POH there will be minus log. You could also use the concentration. You could also use 14 minus our value there for the concentration of acid, and then but otherwise we can just use the minus log since we already have the base concentration. Then that will give us 1.1, and that's our value there for POH. And that's our end field. And then next we have to find the pH. So pH there will be 14.0 minus 1.1. Remember that pH is constant, so 1.1 to give us I think that will be 12.9. So that they will be give us our value for M. Alright, so M is filled up, N filled up also, and then with that pH we know that it's basic. Then we can go in around and then fill in the basic part. Okay, so that part is filled, and then basic there, that is P, that's a value for P, and then that's it. Now we have to so we have a table there complete. So the table is complete. So you can also, if you're not sure, you can double check the problems. So the next thing you're gonna do, that this is gonna be your homework. Once again, you're given concentration there on the first row, so you must fill it row by row, so in that row, pH or H, and see concentration of H, tell whether it's acidic or basic. So you're gonna use all the values. So do this activity so that you be a professional on this chapter. Yes, you'll need to find time. No matter how busy you are, you need to find time to practice. So one part of it is filled, and then you just have to fill in the remaining part. So that is it. So that is A, B, C, D, E, and this is F, that is G, that one is H, and that one is I, J. You have the J there for OH value, you have K there POH, and L if it's acidic or basic, M, N, O, P. So you fill in those spaces by calculation or determination. You can sometimes determine the value, like if you're given pH value, then you can tell that from pH whether it's acid or basic. So other questions are just straightforward, but questions that doesn't require you to put more effort, they're actually simple questions. So that's it. I wish you guys all the best. I hope that this chapter hasn't been problematic. So keep practicing so that you can improve in terms of your speed and all that. And also don't forget to subscribe to this channel for more problems. If you have any problem, please forward to this channel and see how I can help, how I can solve the problem. So that is what I would say. I would say just chemistry is all about practicing and practicing, and also double checking your calculations and see if it makes sense. So what I would say that, wish you all the best. Your tutor is